Okay, so as usual, welcome back. So last lecture, we arrived to define what we call the Smoluchowski-Fokker-Planck equation, which I write again here. Smoluchowski-Fokker-Planck equation is an equation for the probability of observing particle at a given point in a given instant. Right? It's a multidimensional equation, so in general it's three n-dimensional equations for n particle in 3 dimensions, and all that. We verified that it can be written in the form of a continuity equation so even though the Fokker-Planck equation is written in terms of an operator that is not Hermitian, therefore, as we discussed the other lecture, it does not necessarily conserve the number of particles, probability. It's a very special non-Hermitian operator. And this is, if you want, reflected by the fact that the same equation can be written as a continuity equation. And therefore, by Gauss' law, if you want, or by divergence theorem, the flux of the probability outside any surface surrounding the initial condition, say you have a surface that surrounds a final region where the probability is initially condensed, and the flux forward of this probability current, which is defined to be negative d grad, d grad plus grad u with a beta. The flux of the probability current amounts to the change of population within the surface. Right? So this is true, of course, in the most general case in which the initial condition also crosses the boundary of the surface, because what you're really doing is really measuring the flux. And there could be a region where the flux is inwards, and there could be a region where the flux is outwards. Right? There are many things that we're left to understand about this equation. There is one extra piece of information we gathered last lecture, which is that the Boltzmann distribution, P naught of x, or if you want better say the Gibbs distribution, the Gibbs being the most general Boltzmann distribution that does not necessarily concern the microcanonical ensemble, the canonical ensemble as you would imagine in phase space, but also canonical ensemble with fixed pressure, for instance, or like in this case, configuration space canonical ensemble. So let's call it Gibbs, but it's a matter of nomenclature, of course. 1 over the partition function e to the negative beta u. There's no kinetic energy in the Smoluchowski because we cannot define derivative, if you remember. Now, if you plug this current, this solution into the current, you'll discover that the current for the P naught probability is actually 0. This is basically already visible here. The gradient drops exactly the term that cancels the second term. So this function this function generates a null current, and a null current has zero divergence, trivially, and a stationary function P naught is also zero time derivative. So P naught is the equilibrium solution of this differential equation. The Fokker-Planck operator, this term here, H Fokker-Planck, which is defined to be negative of the right-hand side operator there, the Fokker-Planck operator has a zero mode, and by zero mode I mean H Fokker-Planck P naught equals naught. A zero mode is an eigenfunction with zero eigenvalue. So the Gibbs solution is the zero mode of the Fokker-Planck operator, so it's a solution of the Fokker-Planck equation. And this basically closes the circle that we initiated when we proved the fluctuation dissipation theorem, because we said the fluctuation dissipation theorem was proven out of first principle, if you want, but we argumented that it encoded the idea that you need to give up some energy and receive some energy to keep a balance in order to keep equilibrium. Now, the Fokker-Planck equation we have derived has been derived precisely from the structure of the Wiener noise, if you remember. So the amount of kicks we were getting through the diffusion coefficient. So from the fluctuation dissipation theorem, and precisely because the coefficients here follow from the fluctuation dissipation theorem, we have that the Gibbs solution is a solution of the Fokker-Planck equation. If I had put, say, a 2 here with a wrong diffusion or a beta prime there that doesn't correspond to the real beta, right? This would have not had the Gibbs distribution as a stationary solution. So the Fokker-Planck equation, or the Smoluchowski-Fokker-Planck equation, is indeed the fundamental equation that you can think of for describing the time evolution of probability in the overdamped Langevin dynamics, and it's a fully deterministic equation. Partial differential equation. It's fully deterministic for the probability. Of course, the probability is not deterministic in the sense of classical mechanics. Not only that, it's a linear partial differential equation, because the probability appears never at the quadratic order, always linear order. So in other words, you can map these into, if you discretize this on a mesh, it becomes a matrix equation for an array that defines the probabilities, right? So that's a way to say that it's a linear equation. So given that the Fokker-Planck equation is a linear equation, we can use some of the results of the linear equations. And I really want to emphasize that we've been here before in our education, because linear equations pop up everywhere in physics. The Schrödinger equation is, of course, a linear equation, but also the Maxwell's equations are linear. As a result, for instance, you have plane waves, right? Because then you have superposition principles and stuff. Now, in this case, the fact that it's linear allows us, I want to draw, without going too much into the general formalism of linear partial differential equations, for which, by the way, I'm not even an expert, but what I would like to emphasize that we've been in very similar situations a number of times during physics education, and this is no different from other situations we've been before. So let me just remind you that once in your education you were interested in solving the Poisson equation. Now, you might have seen this written differently depending on your convention, if you use the GGS convention or the International Units Systems, SI units. But this is the equation for the potential, right? Electrostatic potential. Well, of course, you're familiar with the Schrödinger equation. And I'm now writing, yes, fine. For reasons, normally it's written the other way around. And now I'm going to write the Fokker-Planck equation. Well, let me write it. H Fokker-Planck, without writing this again. Psi is equal to negative d by dt. Sorry, b, not psi. D by dt. Now, all these equations are normally solved for deterministic situations. That means we want P of t, or in this case we want P of x of t given P of x at some t naught, typically the initial condition. Usually here you do exactly the same. And here you want the source, the electric field, given the source of the electric field, right? The electric potential. And in all of these cases, the way you solve for it is in a two-step procedure. First, you find the Green's function of the inhomogeneous operator, which in the case is a function. So let me just say, first you find the Green's function of the inhomogeneous equation. I'm going to write it in a moment. And then the probability, the solution would be the convolution of the Green's function with the initial condition. Just to be practical, right? When you do electrostatic, you say phi of x is the integral over dy rho of y divided by 4 pi epsilon naught x minus y. Right? But this function, 1 over 4 pi epsilon naught x minus y, happens, let me call it delta of x minus y, happens to be the solution of the equation Laplacian delta of x minus y equals small delta, Dirac delta of x minus y. Right? Physically, normally we are taught that this is the Coulomb potential for a point source, and that the general potential comes by integrating the contribution of all point sources. Right? But the mathematical way to do that is to say that this is the Green's function, the solution of the equation with the delta function on the right-hand side. Right? And then once you plug, and then you use general properties of math, you plug it back, and you know the positions and every time. Similarly, the wave function does a similar story. The probability to find the particle of x of t is the convolution of a quantity that I will call x t z t naught psi of x t naught. And this is the propagator, or the matrix element of the time evolution operator. And it's the solution of the equation Hamiltonian negative IH bar d by dt k x t y t naught equals delta of x minus y delta of t minus t naught. The propagator, or the matrix element of the diffusion of the time evolution operator, is the Green's function of the Schrödinger operator. Okay? And finally, going down one step, we have introduced the condition of probability P of xt given yt naught, and we can think of it as the Green's function of the Fokker-Planck equation. Not the Fokker-Planck operator, but the Fokker-Planck equation, right? Which is this. So delta t, delta of x minus y. So given the analogy of the Feynman propagator in quantum mechanics and the Fokker-Planck propagator, we call them by the same name. They're both propagator, because the probability of finding the particle at x given t at time t is given again by the convolution of the probability of the propagator with the initial distribution. Okay. But we were far better than that. We were able to compute this propagator in a formal way by writing that as a path integral over the stochastic path. And that provided a very nice physics interpretations of the conditional probability as the sum over all possible trajectories, all possible ways in which a stochastic particle can go from y to x in time t minus t naught, each of which with a probability that was set by the exponent of the negative of the Onsager-Markov action. Remember that? So clearly there are some, let alone the electrostatic case, which I drew there, because it's probably the first time you see a Green's function in your education, and you see this idea of convolution, or from this point on we can actually forget about that. There is clearly an analogy between quantum mechanics and Fokker-Planck dynamics, in which, because in both cases you have the evolution of something that is related to probability, written as a convolution of a propagator, with a very important fundamental difference that the Feynman propagator propagates amplitudes and not probabilities directly, while the Fokker-Planck propagator is directly an equation for the probability. So now, today, in the first lecture, we want to address some fundamental questions, one of which is, what do we make of the spectrum of the Fokker-Planck propagator? What is the physical interpretation of the spectrum of the Fokker-Planck propagator, given that we expect it to be important, but the spectrum of the Schrödinger equation, Schrödinger operator, the Hamiltonian, is, of course, the allowed energies of a system in quantum mechanics, which have a fundamental importance in physics. What is the interpretation of the eigenvalues of the Fokker-Planck equation? Second question. What are the eigenvectors or eigenstates, or at least even if we cannot evaluate them all, which is likely to be the case for more cases, what are their general properties? Let me remind you of one fundamental fact. Nota bene. In general, if O is a non-self-adjoint or non-Hermitian operator, the eigenstates of O and the eigenstates of the dagger, let me call it with a different name, are not the same. They don't form a complete set of eigenfunctions, and the eigenvalues are not even real. So we have no guarantee about basically anything. There might be eigenvectors and eigenstates. In general, we cannot exclude this opportunity. But if there are eigenvectors, R of n, the set of eigenvectors, and I'm labeling that with a discrete index, but it could well be that under certain conditions there is a continuum label, like for plane waves in quantum mechanics. But the set of right eigenstates, which are the eigenstates of the original operator, does not form a complete orthonormal basis set of function. The eigenfunctions of the adjoint and direct operator are not the same in general, and the eigenvalues are, in the general case, complex. So I'm just saying that if you violate what's that called? Jordan lemma, if I remember well, is the lemma that says that if you have an initial operator, you have all this nice property. If you violate the hermiticity assumption of the Jordan lemma falls, doesn't apply anymore, and so the statements of the Jordan lemma can be violated. Okay? I remember in my first year, our professor of geometry gave us the proof of the Jordan lemma. It took us 2 weeks. Have you ever done that? So it's an endless demonstration. It's 2 weeks of lectures for one lemma. Proving that the matrix, a real symmetric matrix, has nice properties, that's easy. But proving the Jordan lemma was tour de force. Anyway, I could never do it, so I give this for granted. Now, clearly, if the eigenvalues are non-real, for instance, it's very difficult to give them a physical interpretation. But we have a hope. We have a hope because we have already seen that the Fokker-Planck equation is a very special type of non-Hermitian. The Fokker-Planck operator is a very special kind of non-Hermitian operator because it can actually be written as a divergence of a current, right? Which makes it special among the non-Hermitian operators. So, as we shall see, some of these pathologies that emerge in the general case of non-emission operators are thinned or cured by this very particular structure of the Fokker-Planck equation. And so we will be able to draw some fundamental relationships that will tell us ultimately what the eigenvalues of the Fokker-Planck equation mean. Okay? To do that, it's convenient to further deepen the connection between quantum mechanics and stochastic dynamics, one step forward. And this connection is at the heart of much of the research that I've been doing in my group and other people have done in their groups over the last 2 decades, or even more, because it draws a bridge, clear bridge, between quantum mechanics and stochastic processes, so that many schemes and approaches and methods that people developed for, say, quantum many-body theory can be more or less directly transferred to stochastic theories, providing an arsenal of potential approximations and approaches. So, let's say connection and I'll leave it there because what I really mean is connection between quantum mechanics and stochastic dynamics, but I'm not going to write that all. Okay? Okay, let me start from my beloved Fokker-Planck equation. And I'm going to manipulate this equation. Okay? How do I manipulate that? Well, I'm going to write this equation as negative d by dt, and I'm going to multiply this by the, well, you can say multiply or divide. One way to see that is to divide by the root of the Boltzmann, by the Gibbs wheel. So of course, I'm going to do that here as well. On the right hand side, I'm multiplying this by 1 over root of this. Okay? So I'm going to do this on this side. But this time, rather than using this, I use this notation to emphasize that I'm divided by the root of the Boltzmann distribution, which is the same as to multiply by beta half u of x. Right? Then I have h, Fokker-Planck. And then, you see, let me rewrite this as e to the beta half u of x. I want to preserve again this factor e to the beta half u of x p, because I'm going to give it a name very soon. So all I have to do is to put a negative beta u of x here. Right? Well, this is kind of a familiar mathematical manipulations, because in quantum mechanics, we have often done similarity transformation or unitary transformations, in which we take the wave function, for instance, the gauge transformation is one of them, right? Where we multiply by, say, a phase of an emission operator. And then we transform the Hamiltonian accordingly. So we do if this is emission, it works, right? And then if I know commute, then you have very nice property because you can bring this forward and you basically get the same equation. Okay? Now, this is just an analogy to see that this is a unitary transformation that we have seen already in quantum mechanics. Again, gauge transformations have that structure of the function. But here, this is non-unitary transformation because hell no, this preserve any normalization of anything. It's an exponentially large or exponentially small factor whose sign is always positive, but whose magnification of suppression character depends on the signs of u. If u becomes negative, this becomes suppressing. If u is positive, it enhances the probability, right? In an exponential fashion. Well, you know, whatever. Okay, so we give a name to this structure here. So this is no longer P, because it's a non-unity transformation of a probability, okay? So we give it a name. We call psi of x t equals e beta u, beta half u of x, p of x t. And it's a definition. There's nothing to understand here. And then we give a name, H effective, to this particular non-unitary transformation of the Fokker-Planck operator. Right? Now, I want to make a comment. This we can compute only if we know P, the solution. If we don't know P, we can only express this as a general expression, this factor times P. But as far as this operator is concerned, we can actually expressly compute this operator by writing down HP, because you see, you have e to the beta half u, let me now write the argument. Then we have like negative d squared d plus negative d grad, actually I think there's a plus, d grad u grad plus beta d Laplacians of u grad, and then we have e to the beta half ux, right? Negative. So now we can actually find out what this operator is by simply applying derivatives, right? And never forget that there's a test function here to be applied to, right? Because this is an operator. So when you write gradient here, you mean gradient of this product now, which will drop an application of gradient to this term, an application of gradient to this term, because the gradient is applied to the product of function now. Okay? It's general second year calculus. Okay? Multivariable, or first year if it's one dimension. So this is just to say that I can simply crank a handle or ask ChatGPT and you will tell me what this operator is. Okay? Now let me not do these calculations. In the era of ChatGPT is really something that I don't need to do because it's a trivial calculation. Okay? And let me just tell you what the result is. The result is a new form of a Fokker-Planck equation, this time not in terms of the probability p, but in terms of a new function psi that is related to p by this function transformation. So what is this equation? Well, the resulting equation is the following. Negative d by dt of psi, this doesn't surprise us, we knew it already. And then we have h effective times psi of x. And also, in this case, we're not surprised because all I have to do is to tell you what h effective is. Right? Because this we got already. Well, h effective has this surprisingly beautiful form. So why do I say it's a surprisingly beautiful? Because you see, this operator doesn't contain floating derivatives acting on the probability. It only contains derivatives of u. Right? So this is a multiplicative operator, just like the potential energy in the Schrödinger equation. Right? You give me u, and I tell you what this weird combination d over 4kt squared times all this is. I could have written in terms of beta, but I want to emphasize this subleading with respect to this in low temperature, which will come useful later. Okay? So this is, for all practical purpose, an effective potential. That's right. That's why I wrote that V effective. Okay? And this effective potential has all the nice properties of the conventional effective potential, meaning if u is a function which is bounded, meaning it has positive derivative and never gets to minus infinity, then also V effective is bounded. Why? Because, you know, at large distances you're dominated by this, which will generate a steep rise. And therefore, this is nice and well behaved. It really is nice behaved as a potential in quantum mechanics should be for a spectrum to exist. Okay? So, this means that now I can rewrite this, H effective, in a form that really resembles the Schrödinger equation, the Schrödinger operator, the Hamiltonian of the Schrödinger equation. And H effective, this time, is completely Hermitian. Right? You with me? If you have questions, raise your hands and I'll be happy to answer. So, let's stop for a minute and think about what have we done. we started out with a Fokker-Planck equation, which we like because it has the right solution, but we also don't like because the Hamiltonian is not Hermitian, and this may cause mathematical problems. We don't know, for example, how to expand a function in eigenstates of the operator, as we do very often in quantum mechanics. And we don't know how to physically interpret the eigenvalues of the operator. But however, I told you it's a very spatial operator. And in fact, through the non-linear transformation, non-unitary transformation that I told you, the Fokker-Planck equation can be rewritten, recast into a new form, which looks exactly like an imaginary time quantum mechanics. So we established an exact, rigorous mapping between the Fokker-Planck equation and the imaginary time Schrödinger equation. This, however, doesn't mean that Fokker-Planck dynamics is basically Schrödinger quantum mechanics in imaginary time, because quantum mechanics is not entirely described by the Schrödinger equation. Part of the quantum mechanics architecture is the Schrödinger equation, and then there is the rules to compute probabilities from the wave function, right? And remember, there are two fundamental things. That first, you have to take the modulo square to compute probabilities. And second is this idea of collapse of the wave function, of effect of the measurement onto the state of the system, and entanglements, action at distance, RPR experiments, and all these weird and fantastic and exotic properties of quantum mechanics that we arguably love. I do, at least. Okay. All of that is not here. But the Fokker-Planck equation can be recast as a Schrödinger equation in imaginary time. That's for sure. Okay? Okay, this could only be a nice mathematical curiosity. But it happens to have a much deeper meaning. Because you see, the fact that I can recast the Fokker-Planck equation in a form that contains the Hermitian operators, and I can connect the solutions of this to the other by a simple e to the beta, remember? Tells us everything we need to know about the eigenstates. Why? First of all, the eigenstates. So so since the effective Hamiltonian is Hermitian, we now can claim there is real spectrum and complete set of eigenbases. Okay? So this means that since, okay, let me clear up here so that I can write a string of information without having to sneak in through formula. So the fact that H effective equals H effective dagger implies a number of things. First of all, there exists a complete set of eigenstates of H effective where lambda n's are real, so physical interpretable, and also the integral in dx phi of n of x, phi of m of x is equal to Kronecker's delta m of n. Orthogonal. Remember though Since I have a real Hamiltonian, I can always find a real set of solutions. So the functions as well are real functions. But now I recall that P is equal e to the negative beta half u psi. Why negative? Because I define psi to be plus P. So I'm bringing the exponent on the other side. Okay? So the second property that I want to emphasize is that if I call R of n of x e to the negative beta half u of x phi of n of x, then H Fokker-Planck acting of R of n of x is equal to lambda of n R of n of x. So the spectrum of the Fokker-Planck equation is the same as the spectrum of the effective Hamiltonian. Hence, the spectrum of the Fokker-Planck equation is real. Good. Well, let's continue. Now I call left of n e to the beta half u of x phi of n of x. And guess what? The adjoint of the Fokker-Planck operator times left of n of x is equal to lambda of n left of n of x. I'm basically using this equation, multiplying by appropriate phases. No, they're not phases, they are these factors. And I'm getting this equation, which tells us something about the Fokker-Planck operator's spectrum, and this equation that tells us something about the adjoint Fokker-Planck operator's spectrum. Okay? Why worry about this? Well, it's a very special non-Hermitian equation where the right and left, the adjoints are related by these phase transformations, and they are non-unitary transformations. So they have the same spectrum. It's a real spectrum. And finally, the third property is that the integral in dx of the left of x times the right of m is equal to delta n m. Why? Well, pull off the appropriate factor and they cancel. And use the other property. Okay, so we got it. We got a lot out of there. We got pretty much everything we wanted to know except what we wanted to know. Meaning, we got the math right. Now we need to get the physics back because our interest is in the physics, understanding what these lambdas are, rather than in the mathematical properties of an operator, right? Okay. So what is the physical interpretation of the lambdas and the phi and the r's at all, right? Have you ever done the spectral decomposition of the solution of a Schrödinger equation? Probably yes, but most likely you have forgotten. So let me briefly do it again for you. Okay? So in other words, I'm switching to the Dirac bracket notation. You remember that from your quantum mechanics course, I guess. So the wave function, right, at any time is the ket of a quantum state psi t over position of states, right? Now, I can write that as e to the negative I over h bar h t times the wave function at time t equal naught. Okay? Well, then what I do here, I add 1. And I call this 1 as an identity operator. And I call the identity as the sum over n, the states of the Hamiltonians, the projection over all the states of the Hamiltonian. This is called the resolution of the identity. Remember this? This mathematical expression looks weird if you are not keep on using it after which, but it is exactly the same as when you take a vector in 2D, right? And you say, how do I write a vector in 2D? I project the vector over the first versor, right? So I do v dot epsilon 1, right? And I multiply by epsilon 1. So I get this vector, right? Plus, I project the vector over epsilon 2, and I multiply by epsilon 2, and I get this vector. Right? Now, if instead of using this symbol, I was using this symbol for inner product, and instead of using this symbol for vector, I was using the ket, just a notation. Sorry, I've done something wrong here. Saying epsilon 1 v epsilon 1, and I was doing epsilon 2 bra epsilon 2 v bra ket epsilon 2, right? I'm just using a slightly different notation. Then this would be v equals sum I going from 1 to 2 epsilon I apply to V. Right? This goes there, gives me this, and I'm multiplying by this. See? So this means that this is nothing but the identity, which for two-dimensional is what this is for Hilbert space and dimensional Hilbert space. So I can do this. Okay? This is my review of quantum mechanics 101. Now, if I do this, this would be sum over n x. Now, you see, what I would get here, I would get the Hamiltonian that acts on its eigenstate, right? Now, if you have an eigenstate of h, it's also, you can build the eigenstates of e to the IH, right? Because this is just a Taylor state of h, and h commutes with itself. So this will be e to the negative I over h bar, lambda, sorry, yes, let's call it epsilon of n, h, n, epsilon of n, n, right? The energies. T, and then I would have n, and then I would call this Cn, where Cn is the ket, the bra of n with the Cx naught. So this is an initial condition, how the initial state overlaps with the nth state, right? So, last step, I can write this as sum over n, the famous story that you have the sum of the phases when you solve the time-dependent Schrödinger equation. And then this and this becomes the wave functions, the eigenstates psi of x, psi of n. So, the wave function at time t is decomposed as the sum over all the eigenstates, weighted by a specific factor that contains a phase with the energy and a coefficient which depends on the overlap of the initial state with the initial states. Right? This is called the spectral decomposition of the wave function. Okay. So let me write it here. I'm just write the results that we just wrote here. Here. Sum over n e to the negative I. Oh, there's an h bar, there it is, and c, cn, phi of n of x. Okay, I'm going to erase this. And now I can use this beautiful math to solve also the evolution of the R of n, the right eigenstates of the Fokker-Planck equation. Why? Well, first of all, because the first step is to go from the real quantum mechanics to the imaginary quantum mechanics, right? So this means that now the line below is the side that enters the quantum mechanical formulation of the Fokker-Planck equation, okay? Which is an imaginary time Schrödinger equation, which basically is x e to the negative h effective t. I can still introduce a bra. I mean, nobody prohibits me to use a Hilbert space for stochastic dynamics. There is nothing that says only quantum mechanical states need a bracket notation, right? And then my state times 0. In other words, I can say this is sum over n e to the negative lambda n t c of n phi of n, where now c of n is the overlap of the initial pseudo wave function with the nth state of the effective Hamiltonian. But now we are basically done. Because you see, now all I have to do is multiply by e to the negative beta u half, and I get the solution of the Fokker-Planck equation. Right? So now I can basically skip all this and say the solution of the Fokker-Planck equation is a sum of some frequency scales times the right eigenstates of the Fokker-Planck equation, times some coefficient Cn. And Cn is equal to the integral of dx of left n x, and then the probability of x naught. You with me? But this is kind of cool. Why? You know, don't forget, we know C naught, we know lambda naught. Lambda naught is the lowest eigenvalue of the Fokker-Planck equation. How much is the lowest eigenvalue of the Fokker-Planck equation? Remember, we proved it before, when we proved that the Fokker-Planck equation could be put into the form of the continuity equation, and that the Gibbs distribution was the solution. We call it a zero mode, remember? Huh? So it's zero, which means that nothing changes over time. So let me write this. So the spectrum is lambda naught less than lambda 1, less than lambda 2, and so on and so forth. These are all positive. Right? So I can write this as C naught R naught of x plus C1 R1 of x e to the negative lambda 1 and all others, but all of these will be exponentially suppressed with respect to this. Right? Because they fall off exponentially with a larger exponent. Agree? But there's an additional thing. We know already what R naught is. It's the Boltzmann distribution, right? So this is C naught 1 over z e to the negative beta of u of x plus C1 R1 e to the negative lambda 1 of the plus all the others. Finally, exercise C naught equals integral dx L naught of x right naught of x. Right? But now if you remember, L naught and the right naught are connected because one is e to the beta u of the other. The result of the results can show this is 1. So C naught is actually 1. Because of the properties. since this is the Boltzmann and this is Boltzmann time divided by Boltzmann basically, and then you have 1 over z, and you can work it out. Oh, okay, let's do this. This is dx phi naught e to the beta half u, and this is e to the negative beta half u times psi naught, right? But psi naught is 1 over root of z e to the beta half u. So if you do all the calculations, what you get an integral of the partition function divided by the partition function, which is 1. So now we have arrived to these very, very beautiful equations that I'm gonna erase this line and copy this line here to make it a little bit more visible. So what are we saying? We are saying that this is the Boltzmann distribution, or the Gibbs distribution, plus corrections let me say all the sum of all the eigenvalues greater than naught, all the others, right? Which may be positive or negative, because you know the node theorem that says that the wave functions, the nth wave function has exactly n nodes, right? So it goes positive and negative. So the same applies to the R's. So this contribution here is overall positive, but the individual terms can be negative. Okay? So now we understand. This expresses the solution as what remains after infinite time has passed, and it's the Boltzmann distribution, the Gibbs distribution. And these are the corrections that appears during the transient time where you're doing equilibration. So that means that lambda i's has an interpretation of thermal relaxation frequencies. Why thermal relaxation frequencies? Because you get the Boltzmann distribution when the time is much longer than the lowest non-nil eigenvalue, right? Lambda 1. When t lambda 1 is much greater than 1, e to the t lambda 1 is 0, and you're left with Boltzmann. So lambda 1 is called the thermal relaxation rate. Is the rate 1 over lambda 1 is the thermal relaxation time. How long you need to wait for the system to attain equilibrium. So all information about the kinetics by which you reach equilibration is contained in the spectrum of eigenvalues of Fokker-Planck operator. Finally, we got our mission done. We understand what the spectrum of the Fokker-Planck operator tells us. Okay? Questions? I want to make one comment. There's a yet another fundamental difference between quantum mechanics and Fokker-Planck dynamics. The energies, the eigenstates of the Hamiltonian are defined up to a constant, aren't they? Because all that shifting the ground state energy does is to introduce a global phase to the wave function, right? Or shifting the eigenvalues. So in other words, the H going into H plus C, or the energy H of n going to energies plus C, which means that all the phases here pick up an overall phase that multiplies the sum because it's the same for all states. And when you take the modulo square, you don't notice it. But this is quantum mechanical way to say we cannot define energy in absolute term, we need a reference term, right? Well, this doesn't apply to the lambdas. The lambdas are not defined up to a shift. The lambdas are what they are. If the thermal relaxation rate is 5 minutes, it's going to be 5 minutes, period. So it's not the relative lambda that is important, because the lowest lambda is fixed by the condition to attain thermal equilibrium, and it's going to be 0. Otherwise, your probability will disappear, and the system will not describe a conserved number of particles. System of equations. What about the other lambdas? Where the other lambdas will implicitly, in a very implicit way, encode the information about faster relaxations. And to get a grasp of what faster local relaxation means, let me resort to your physical intuition. Okay? Suppose we have an energy landscape done like this. Now suppose we put all of our particles in the leftmost well at the beginning. So we put n particles here, all say in the same point. Say we put it, maybe we put it here. Okay? So which means, if you want, if you can think about this as repeating the experiment many times with one particle, or having n particles that don't interact with each other, all at once throw in a time naught. Right? If n is sufficiently large, the distribution of position of n describes a density, right? And therefore we can imagine that the initial distribution, for instance, is this. Right? First of all, let me emphasize that the fact that I put the particle here doesn't mean that the particle is going to roll up to this point in the energy. Because this is true only for inertial dynamics, but there's no inertia here. Right? This is overdamped. So typically what this will do will drift to the bottom and start wiggling around. Every so often it will get a number of kicks on the left, on the right, on the left. Okay? But quite rarely, in fact exponentially rarely, as I will argue in a minute, you will get a series of kicks that will drive you in the right direction. Maybe here, 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 here. And this is called the transition state, TS. And let me label TS1 because there are more than one here. Once you pass the transition state and you're wiggling around, you're very likely to roll off this well. Right? How often do you cross the transition state? Well, this is done. You can invoke Arrhenius theory if you remember something from your chemistry course. But before I invoke Kramer's Arrhenius theory, let me just convince you that this is an exponentially long time in the height of barrier. And you can do that in a very crude model. Let's assume the particle can move to the right and to the left. Now, this is okay in 1D. And since it moves because of energy kicks from the environment, right? Its energy will not stay the same. On average, you will get, say, kT from the environment, okay? For kT, who cares? Say kT, okay? So let's say every time we move by an amount that shifts the energy by kT, right? So for instance, if you happen to be in the bottom and my barrier is, say, 1, 2, 3, 4 kT, right? I need 4 kT, I need 4 kicks all in the right direction to get to the bottom, to the top of the barrier. Right? So every time I throw a dice, I have 50% probability to get in the right direction or in the wrong direction. And I need delta U over kT tosses in the right direction, right? So if T naught is the time between a toss and the other, the typical time scale of microscopic dynamics, the time for transition in this extremely crude model would toss like 2 to the delta U over kT, right? So it would be times I naught. Why? Because every time, because the probability will go down with like 1 over 2 to the delta over kT, and in order to get this probability of an event, I need to have 1 over probability number of attempts, right? And each attempt lasts T naught, the total time would be like that. This is an extremely crude estimate because, first of all, I'm not accounting from the fact, first of all, not all the kicks are exactly kT. In fact, they're not exactly kT half, to be precise. But let's not be too precise, okay? But also, I'm not counting for events that like 3 on a row, 1 bad, and another 2 on a row. This will still make it to the top of the barrier. So if you do things very carefully, you'll discover that T actually is some time scale that I will not worry about, but depends on the frequency here and here. And e to the minus e delta U over kT, where delta U is the activation energy. Well, how much, so what I want to say is that every barrier crossing will take activation energies that are exponential. So for instance, this barrier crossing will take a time that is very different from this, for instance. Right? Conversely, the local relaxation time is such a much faster process because it doesn't have to explore thermal relaxation. We can do an exercise and estimate that from the Fokker-Planck equation for an harmonic well. It's probably an exercise that would be worthwhile doing, understanding what is lambda 1, the longest relaxation time in an harmonic oscillator. It's very easy to do. I will not do it today because this is a little bit of too math. It's very simple, but it would drag me away for the rest of the lecture. Okay? But believe me that the thermal relaxation within the well is a very fast process. Right? So what happens to the system? If you drive it somewhere here, this is not in equilibrium because this is not the Boltzmann distribution. It will first build a distribution that looks like the Boltzmann distribution of this well, completely ignoring the fact that there will be a barrier and therefore that there's a universe past the barrier. Right? But if I wait long enough, and specifically I wait the time scale of the order of a mean first passage time through the top, through the transition state, I will start seeing a population pop up here. And the particle will quickly relax here. And then it will take another longer time to cross this very small barrier. And a much longer time to cross here, but I'm not done. Because equilibrium means ergodicity, I need to be able to go back and forth many times. So also these time scales will be important for ergodicity. So what I'm trying to come across with is this very fundamental idea of kinetic theory that the spectrum of the Fokker-Planck operator is characterized by long, slow relaxation processes induced by the barriers, right? And fast relaxation processes. Lambda 1 is the frequency. None of the lambdas are not identified with any of the barriers. Lambdas are global concepts. But if as we shall see later, we can relate the number of slow lambdas or small lambdas to the number of barriers. But you cannot say lambda 1 is the largest barrier, lambda 2 is the semi-largest barrier. Well, you can only insert an asymptotic limit. Okay, in general, you cannot do that. But what is important to say is the system first locally relaxes, and then population starts to rise, and then back processes start to emerge until all of a sudden nothing changes anymore. Not all of a sudden, actually, the opposite of all of a sudden. Then very, very slowly, this decays into static distribution. So all the lambdas that enters in the spectrum carries about relaxation times, and there are some slow lambdas that are associated with slow relaxation times, and some fast lambdas that are associated to fast relaxation times. And if there is a gap, if there is at least one barrier, the spectrum of relaxation contains a gap. Right? So, in particular, here there would be an infinite amount of fast relaxation process, a gap, and an amount of slow relaxation process. And in the next hour, we'll take a break now, and after that, we will introduce some ideas about how many of them there are. But there's a gap. In other words, lambda soft I minus lambda soft k in modulus is much smaller than lambda hard I minus lambda j high. Any difference here? These are widely separated frequencies. Here are all piled up small frequencies. Why they're very tiny grain? Because they are numerically small. So here's the ground state, and all of these are small frequencies, right? So the difference between two small numbers is small, the difference between two large numbers is large. Okay? Okay, I think I'll stop here for a few minutes so you can take a break. And then we do another 45 minutes or so. Okay?